Okay, this is a rather haphazard demonstration of the different kinds of error which can be induced in your probe leads if you aren't careful to keep them at right angles to the primary winding on the transformer. So here I have the approximately 1 volt per turn 41 kilohertz oscillator. It's 10 turns a number 4 wire. Here I have my little demonstration bulb. It picks up the voltage and lights the bulb. Here I have, it's just 10 feet of number 10 super flexible wire, so it's easy to mess with. And it's just a single piece of wire, and the two ends go right here into this voltmeter, which is set to 2 volts AC. And let's get started. So I guess I can take this out. Well, now you see, when you see that there, you know there's power. Okay, so first of all, I'm going to show you one turn of voltage on this coil is about there. It's about 0.6, 0.7 volts per turn at the top. I can get better coupling by going around the outside and pulling this up tight, and see, then we get about 0.9 volts. And I can go around a second time, and there's like little 1.6, 1.7, so that's about double the 0.94 or whatever we had. So this voltmeter is actually not rated for 40 kilohertz, but it essentially works, so I'm using it just to illustrate this. So let's start out. Let's say we want to measure the voltage across these 2 points. This is a piece of wire. It goes straight through here, and as you can see, there's no voltage across this wire because this wire is at right angles to the primary here, and here, so there's no voltage induced in this wire from the primary here. Now, there could be a voltage induced into this wire from the primary here, but the problem is the exact opposite voltage would be induced from this side, because this is the same distance and the same current and everything, so it's identical. So in the middle is a null zone where there's no induced voltage, and I can actually demonstrate that with this. See, I can move it all around and I've got power, but if I turn it up on edge in the middle, it goes out. If I move it over here, I might be able to, sometimes I can get it to light up. See, I get it to light a little bit there. And the same thing over here. But in the middle, it's the null zone because all the induced voltages cancel each other out, and the magnetic field is basically neutral on this axis in this area. So by putting this straight across here, this is running at right angles to the coil here and is equidistant between these two, so the magnetic field is canceled out. And you can see we have 0 volts. Now, I'm going to twist this on here. Now, so the question is, let's say we want to measure the voltage on these 2 points. Can we just attach these 2 points, wrap this around like this, and twist this up like this? And the answer is obviously no, because look, we're getting almost half a volt of reading now, even though we know, I should hold this in here like this in the center. We know that there's no voltage across here because Faraday's law requires that no voltage can be induced in there because of the geometry to the primary, and we measured it, so we know that there's no voltage in there. And our light bulb confirms that no voltage will be produced in that axis. So, and yet we are measuring voltage. So, and it doesn't matter if this is just parallel or twisted. I mean, it makes slight changes there, but the point is these are close together, so there's not really any voltage induced in this area. So what's happening is there is almost 1 volt per turn of induced voltage around this winding, the primary. And because our probe lead follows this path, according to Faraday's law and observable reality, it has the exact voltage induced in our probe lead as is induced in the primary. So we get 1/4 of a volt here and 1/4 of a volt here induced into our probe leads. So whatever the actual voltage is here, we'll have this much added on or subtracted. The way around this is to follow the same rule we just discovered and keep our probes at right angles to our primary. And when we do that, there's no voltage induced in here because, remember, the magnetic lines of force are going around like this, and this, and this, and this, and all around, and this red wire does not cut across them when it's like that. When it turns and goes like this, then it is cutting through the lines of magnetic force, which I'm trying to show with these pieces that twist out here, but see, it's cutting through the lines of magnetic force, and now we're getting a reading. So the more we have following here, the higher the voltage gets. And it doesn't matter if we come over to this side and join up, or come around in the middle and join up, or come around to this side and join up. Now, you might say, ultimately, these leads do need to come back together, because the problem here is when these leads come back together here, they follow this path, and they have this voltage induced in them, and we see it on the meter. So I'm saying we keep the leads straight away, and that solves that problem. The obvious catch to that is that at some point these leads have to come back together to come back to the same voltmeter, otherwise they won't, we won't be able to measure the difference between them on a single instrument. And if this solenoid were infinitely tall and infinitely deep, then it could be difficult to get far enough away maybe to get out of its magnetic field. I don't know, I've never tried a long one, but this one's only like 2.5 inches tall, so its magnetic field only extends a small ways and it tapers off really quickly outside. And I'll show that with this. See, inside we've got a pretty uniform, pretty strong magnetic field, or flux field. But as soon as I start to get outside, it gets really weak. It's not even enough to light the bulb. And so out here, that field is very weak. It probably falls off with the square inverse of the distance or something, because it's getting, weaker this way, and then it's also just spreading up and down and right and left, so it's, like light falling off with the square of the distance. Inside here, it doesn't fall off with the square of the distance, because this is focused in kind of, so it falls off, but it also concentrates. So, well, I'm probably not saying that right, but it's relatively uniform inside. So we don't have to run these leads out infinitely far away. All we have to do is run them out far enough that they get out of the bulk of the magnetic field from the coil. Then we can run them back around. Let's see, can you see that? Yeah, run them back around and join them up. So Can I do this? See, I'm getting, at this distance, I'm getting, let's see, can you see? Oh, I know what I'm going to do. I'm going to turn this way, move this over here, move this here, and now maybe you can see how this goes better. Oops. Okay. I need to loosen this and slide these a little bit. Okay, can you still see everything? Alright, there's the voltmeter. So you can see our leads do rejoin each other right here. But just because of this distance, the distance between the primary coil and where they rejoin, you can see our induced voltage is actually very low. I might be able to pick, if I go 10 times more sensitive, I can pick up 40 millivolts. So there's a little bit induced. If we made this farther, you know, we could get it less. But the point is, I can get it down to the point where it is an insignificant source of error. And in fact, with this 10-foot lead, I can actually move it much farther away and reduce it even more. So can you see how that, oh, it's not all fitting, but, oh, there we go. Okay, see, that's where we're starting to pick up 0.001 volts. But if I were to tighten this up, and go, here's our half, put it back to our half of a turn, see, now we're getting our roughly half of a volt. Of course, if I go like this and get a full turn, then I get closer to our full volt, especially if I couple it correctly. Like around the outside was better. But anyway, so in summary, one way to probe without inducing voltage in your probe leads is to fly them straight out. Another way is to fly them straight in, which, let's see. Yeah, I think I can. Okay, so is this gonna work? I bring them right straight back to the center. So if I tip it over, then I get an induced voltage. But if I keep it upright, and I bring them straight towards the center and back then as a twisted pair or coaxial or whatever, or just close to each other, then you can see, again, we have no voltage induced in our test leads. Now, so far, we've been measuring the voltage on these two pieces, or these 2 points, based on, you know, the zero voltage. We're using zero voltage as a baseline, and so that we can see when we have induced voltage in our leads, because obviously there it is. See, I can add as much induced voltage as I want by just going around and around. And as many times as I go around, I just keep adding up the voltage. Oops, over range. But anyway. So now let's actually measure a segment of, okay, we're actually going to measure some voltage induced on our winding here. So I am going to fix us to a half a turn here. For this demonstration, where did my other crystal go? There it is. For this demonstration, we will be actually running our wire along 1/2 of our solenoid. So there's 0.3, 0.4, it's about half of our 0.7 that our total loop was showing earlier. If I go for a full loop, it's about 0.7 something. So half of that should be about 0.3 something. I guess 0.4 on a good day, huh? Okay. Now this is correctly probed. We are measuring the actual voltage induced in this half of a turn right here. There's no voltage to speak of induced outside this point or outside this point. Well, there is on that because it's not going straight out. But as long as these are going straight out or straight in, see, we could also go straight in, bring them to a pair, and then run the pair out. And that's a lot of times easier. But for this demonstration, I'm going to go straight out. So when we're going straight out, we have no voltage induced in these leads, but we have our 0.4 volts induced in this lead. Now, if we're not careful with our probing, two things can happen. If we say, well, we'll bring the voltmeter over to this side, look at that. The voltage goes back up to our 0.7 because we've just added in another half of a turn of inductance, inductive coupling to our leads. But this is not the true voltage that we're measuring here and here, because this is after we've added in the voltage induced in these leads here. So we have to be careful of that. The other thing that we can do is we can say, well, we'll put our voltmeter on this side. Look at that. We don't read anything. How could that be? Well, if you look at Faraday's law and Kirchhoff's law, you see that we'll have plus half a volt or so, I guess 0.4 volts induced in this inner loop. And then we'll have that same voltage induced in this outer loop because they're following the same path essentially. And it's like when you take two AA batteries. Hold on, let me grab a couple. Okay, are we back? Yeah. So let's say you take, see, do these show up? Yeah, these show up. You know, if you take two batteries, these are each 1.5 volts. You put them in series, you get 3 volts, right? Let's say you put them this way and measure. They're each 1.5 volts, but if you measure across here in DC, what will you get? And the answer is 0, because the plus 1.5 volts of one of these subtracts from the minus 1.5 volts of the other, and so you end up with a difference of 0. And so that's the same thing that's happening here. Imagine, if you will, a little battery like this and another little battery like that, and see, the plus connects to the plus, and you go to measure across here and you won't see anything because they both cancel each other out. So, and I'll demonstrate, I don't know if those are good, but I'll demonstrate that in a bit. So if we double our probe wires back on each other like this, we're not measuring the voltage here and here. We're measuring the voltage here and here minus itself, basically. So it cancels out because we're getting this voltage induced in the inner loop and then uninduced canceled out because it's also induced in the pathwise opposite sign in this outer loop. In other words, if you were to measure from here to here or here to here, this would be the plus in both cases. But if you follow the path, it's going out here, minus, plus, and then plus, minus. So as you follow the path, it changes signs when you switch from the inner to the outer loop. So this is the other way that we can add probing errors. And of course, as you might expect, if we fold this like this, then that reads about the same. Okay. that reads about the same as going straight out, see? And the reason is, again, remember I showed you could take them both into the center, join them together, and then make them go wherever as a pair, a twisted or shielded or whatever, close pair. Or we can go straight out, or we can have one straight out and the other across and straight out. Again, this is going through the center where the magnetic field is at the null point. See, we bring this up and the bulb goes out right there. And so this has 0 induced in it. And then, of course, here it's still at right angles to the primary, as is this. So these both have 0 induced into them. So this is a valid probing configuration. This is a valid probing configuration. And we can even join them in the middle and then go straight out there. Actually, once they're joined in the middle, they can go any which way, see? It doesn't matter then, because they anything induced in here cancels itself out because they're a pair. So let's see, did I get everything? This is kind of neat though, really, because you can do one turn. You can do any fractional amount of turns as you want. So I can go down and do one and a partial turn. Let's see, I'm going to go around again. I'm going to see if I can get it to exactly 1 volt. Yep. So by putting on about a turn and around a turn and a half, I can get it right to exactly 1 volt. But anyway, that's why it's important to keep in mind the magnetic field around the secondary or the primary and the effect it will have on your leads. And in fact, even if just part of your lead comes and passes by, see, it changes the reading. So there we're at 0.4 volts. I take one of my leads and put it by here, and I can cancel out that. Or if I take and rotate it and put it up here, then I add to it. So the basic rule to remember is Faraday's rule, and it's very simple. If a wire is passing through a varying magnetic field, a voltage will be induced in that wire that's proportional to the rate of change in the strength of the magnetic field and the whether it's on axis or off axis. So if I turn this way, then it doesn't have an effect. Not much of an effect. Well, it's picking it up because I'm moving that, but I'll show that. Well, I showed it already, but I'll show it again. Okay, so see, I've got no induction there, or no induced voltage there. And if I hold, see, I'm holding it vertically at right angles to the wire, and no induced voltage there either. Any angle that's at right angles and centered on the primary is in the null zone. So I can move that all around. Any angle that runs the same path will have induced voltage, see? And the, this will be interesting. The amount of induced voltage is also dependent on the angle. It's like the sine or the cosine or something difference. So I just made a nice multi-turn coil here. So here we have 0 because that's at the non-sensitive axis. And see, the more I line it up, the higher it gets. The higher and the higher and the higher and the higher. And if you were to look at that, it would be like the sine or the cosine of the angle, depending on which way you're looking at it. And that, in fact, is why electric generators tend to put out a sine wave. Okay, let me get my voltmeter leads and see if these batteries will demonstrate my little subtracting principle here. Okay, so these batteries have 1.48 and 1.51 volts. Okay, they're not fresh, but as you know, we'll put them in series and measure. Oops, gotta be smarter than the battery. See, 3 volts. Now, what happens if we turn them back to back? The 1 point, what was those two numbers again? Let's just get a calculator going here. One of them is 1.48, so 1.48. The other is 1.51 minus 1.51. So if we put them back to back and measure them, look at that. We get 0.03 volts of difference. So our voltage is almost gone. If they had identical voltages, it would have been read 0. And that's what happens when we have a winding that doubles back on itself. It's just like this. And then we go measure it out here, and we don't read anything, and we think there's no voltage there. Well, the answer is there's voltage there, but then there's also the negative voltage there. All right, that should cover it.